And also one thing that I want to mention is that, especially thinking about these times, in some way challenging. Hopefully we are at the end of it, or we are getting out of it. But geology is really like the opportunity. Studying geology is traveling the world. So you can actually study geology and go and discover in these places that you could never think about it before. How much reading like the article at Field et al. That you gave to us, it's kind of, I was reading, I say, how much we don't know about things around the world, especially like this kind of native people that were in this island that unfortunately basically got extincted because they were killed. Like all the men were killed while the women and the kids were transported somewhere else. So it's sad, but like if I wouldn't have read that paper, I would never kind of know the kind of things that in 70, 80, a native tribe was basically canceled from and that is because of like market of flowers of animals and probably fishing and things like that. So I don't know if I said everything, but like again, like it's an honor. And I know that you have accomplished a lot. You have been in many like scientific research project, and like the one from the paper. So you had like some accomplishment in terms of funds, but also in terms of publication, and also you had a lot of teaching awards during your career. So I don't know. I mean, like, just looking at your profile, it's oh, I want to be like that. Like the song of the Book of Jungle that my son is watching right now, and there is a song that says like, I want to be like you. And so and a total like inspiration figure.
That's so kind, Rosario. But I want to make sure we have time to talk about the volcano.
Yes, sure.
I really appreciate those kinds of things.
What I'm gonna do, I'm gonna share. No, I'm gonna allow the sharing so that you can use it. And okay, now you should be able to actually share. And so, with no further say, I'm gonna shut up.
Okay.
Welcome, Kirsten, and it's all yours.
Thank you so much. I guess, well, the first thing I'd like to do is I would like to acknowledge that I'm speaking to you from the ancestral lands of the Walla Walla, Cayuse, Umatilla, and Nez Perce groups of people. And I also would like to acknowledge that I've been very fortunate to work in the Aleutian Islands, which are the ancestral homes of the Unangan or Unangach people, more commonly known as the Aleut people, and especially the tribal group, the Akugan, who did live on the islands of Four Mountains before colonialism really meant that they were erased basically from the earth, and their history never had a good chance to be recorded. So I'd like to pay my respects to elders past and present of the indigenous peoples I've been fortunate enough to meet and to work with in various ways. As a quick aside, I would like to let all of the undergraduates know that I grew up in a small town in Wyoming. I actually spent the first 7 years of my life living on an isolated ranch. And because of this, the idea of travel and the idea of mountains, because this ranch was dry and had lots of sand dunes. So the idea of mountains was always very appealing. And I was introduced a little bit to the French language at an early age. And so at Colorado College, I minored in French. And I did that because I wanted to study abroad, which I did, go live in France. And I did that purely because that seemed like an appealing thing to do at the time. But the study of an additional language actually opened a tremendous number of doors to me. And since that time, I've also worked to learn Spanish at a very, I'm not proficient yet, but I'm getting there. And so I do want to say that my liberal arts education was absolutely crucial to these many opportunities that I later had. So good job for choosing Colorado College. All right, I'm going to present a lot of science today, and I am here acknowledging Mitsuru Okuno, who is one of my collaborators in Japan, and Pavel Izbekov, who himself has indigenous roots in Siberia, actually people closely related to the people who would have inhabited or migrated into these islands. And they've been wonderful collaborators, and there are many more. So I should indicate to you that all of the work I am doing today has brought me into contact with approximately 40 to maybe even now 50 different researchers, which is just completely exhilarating intellectually. Okay, my story with Mount Cleveland, which is probably more appropriately called Chuginadak, but it's on the maps as Mount Cleveland. My story begins when I was at a workshop in the summer of 2001. And I was there to learn a little bit more about remote sensing, like this top right image that you see from John Dean. But he knew I had done my master's on an adjacent island and had an ongoing project. So in the middle of this workshop, he says to me, "Do you want to go to Cleveland?" And I looked back at him and said, "Ohio?" And because I had never really heard of Mount Cleveland, in spite of the fact that it had had two very substantial eruptions just a few months before. This is not uncommon in the Aleutians. For even those of us who are experts to turn to each other and say, "Have you ever heard of that volcano?" And everybody will shake their heads. Well, Mount Cleveland really was opening up the throat of its magmatic system in 2001, and since that time has had many, many eruptions, with a very significant eruption in 2008. So with John Dean and others from the University of Alaska, Fairbanks, I spent 2 field seasons on the islands in 2002 and 2004. But it is very difficult when you have a 12-day field season because of weather, because of transportation difficulty, to study a 5,000-foot volcano on foot. And so that's going to be a theme that you'll see. Okay, so why did I say yes, other than the adventure, which was definitely part of the reason? And in this North Pole view of the Aleutian Islands, we are going to learn a little bit, I hope, about how the magmatism of these islands really reflects a lot of tectonic complexity and change through time. And that was my initial interest in these islands. But I would say now my interest is as much or more in the story of the people and prehistory with the Holocene volcanism. So we're going to start off here. And just as a little introduction now, looking at a more typical view of the northern part of the Pacific Ocean, you see the Aleutian Islands, which stretch more than 2,000 kilometers from the tip of the Alaska Peninsula. And we don't really even know how many Holocene volcanoes there are. We can guess, but there are still volcanoes there where geologists have not collected samples. One of the reasons this area is so interesting is because the large mountains of the Alaska, Talkeetna ranges are constantly shedding sediment into the Gulf of Alaska. And the subduction of the North Pacific Plate beneath the very enigmatic area of the Bering Ocean, or the Bering Sea, is oblique. And it means that over here near Kamchatka, we have very orthogonal or direct subduction. And consequently, the volcanoes of Kamchatka are quite lively these days. But as we move along the Aleutians, we go from an almost orthogonal convergence in the eastern part, closer to Alaska, to strike slip. So that's one major difference. The other is that we have some sort of enigmatic transition here from what we would typically call continental crust, or a continental sort of dominated plate, to really an intraoceanic arc. So I'm going to get into that some more. So we have this intraoceanic subduction zone geochemically that makes some of our studies more tractable or simpler to understand. But we have this transition in plate thickness and potentially plate composition in terms of the lower and middle crust. And we have a very long history of magmatism. People think that there have been about 3 pulses of robust magmatism, but really I would say our sampling is not good enough to really understand that 38 million year history of magmatism. We're only now really starting to understand the Holocene part of that story in some places without having had a chance to even look back into the Pleistocene. So, okay, so what is subducting? We should be thinking about that. And this is a schematic where these lines that say 25, 26, 27, those are indicating magnetic anomalies of the ocean crust and telling us that the subducting oceanic crust is relatively young for this arc. The other thing we see here is that there are 3 prominent fracture zones. And these fracture zones have been exposed to ocean water long enough to really soak that water up and create very deep hydration of the crust along those fracture zones. We'll also see that the largest of these, the Amlia fracture zone, really marks a boundary where we have more sediment going into the subduction zone and less. And the other thing that I would like to point out in this image is that the youngest volcanoes are typically displaced to the northern part of the overriding plate. So the orange rocks here have a complicated history. This is subaerial island mass, but the Holocene volcanoes are northward of that. However, in the islands of 4 mountains, this little group, we have a really unusual situation. The volcanoes, there are several big Holocene volcanoes that are really close together. And that's actually the focus of a proposal I just submitted that I'll talk about at the end. They're also closer to the trench than some of these other volcanic areas. So the crust is very young, sorry. I will continuously kind of talk about how things are changing along longitude, and the sediment supply varies longitudinally. And then these quaternary volcanoes are north of older rocks. Okay, this is just a quick introduction from Peter Kellerman showing his estimate of sediment thickness with longitude. So the Alaska Peninsula would be over here on the right-hand side of this diagram, and the Aleutians would stretch across this diagram horizontally, and Kamchatka would be off the edge on the left-hand side. So I'll show those kinds of figures. And what you see is that the sediment going into the subduction zone is really high, both because alongshore currents are bringing it down toward the Aleutian Arc, and because the Amlia fracture zone, which is placed about where this blue line is, actually may form kind of a barrier to that sediment continuing further westward. And so it kind of piles up there. Okay, and this fracture zone is not very dramatic when you look at maps of the ocean floor, and you can't exactly see the sediment piling up. For reference, here are the islands of Four Mountains. So they would be, roughly speaking, right in this part. Okay, the Amlia fracture zone, we can see where it is right now today, which is considerably further west, as I just showed you, than the islands of Four Mountains, which are here where Chuginadak is. But because the subduction is oblique, not straight on, it has a westward component, we can calculate back where the Amlia fracture zone was in the past. And it actually, this is a little out of date. We know that it was parked here for several million years, actually, before it started moving westward. You also see that because the Earth is a globe, and because of the nature of the subduction, people talk about the overriding plate having broken into fragments that show strike-slip faulting in between. And I happened to experience a couple of these really big earthquakes, which were entirely fun, mostly. So, okay, so how did I get started? Actually, I got started in the Aleutians for my master's project. I went to University of Wyoming for my master's, and Jim Myers had an NSF-funded project to look at UNASCA because he was interested in this continent to oceanic arc transition, and because there was this strike-slip zone nearby. And so I worked on this very young caldera. Here, we were the first geologists on the island. We made a provisional map of the caldera, and I put together a chronology where we talked about the sequence of eruptions, and then the youngest caldera forming event, and then post-caldera units. And you can see the post-caldera cinder cone and a flow that breached the rim of the caldera, as well as these cliffs expose a poorly welded ignimbrite. So the difficulty is trying to figure out when any of this happened. We've tried argon dating. These rocks are by and large too young to return in Argon age. And I'll come back to that idea of the difficulty of a chronology. So again, I'm looking here with longitude, and I'm looking at age. And if you are interested in people, or if you are interested in understanding the Holocene history of a volcano, so you can think about future hazards, it's really helpful to get an idea of the periodicity. How frequently are there eruptions? And so on the y-axis here, I have 0 being today, and this is basically the Holocene with older eruptions at the top. And what I did was a student and I compiled everything we could find in 2013 about the nature of explosive eruptions in the Aleutians. And this was directly because of a question from a Japanese researcher who worked, he was a volcanologist who worked with archaeologists, and he was astonished at how little we know about the Aleutians. Well, notice, this is the region where Cleveland is. There are at least 6 unstudied volcanoes, or at least prior to 2014, I had been to Cleveland twice. And other than that, we had a handful of rocks that fish and wildlife biologists had picked, one from each island. And we didn't even know where they picked up those rocks. So when I went to Cleveland, I got to see fantastic geology. I mean, just a beautiful lava flow with a flow-based breccia. I've thrown this in because you're a volcanology class, but it also gives you an idea of how we had to scramble around. There were 2 of us trying to sample an entire volcano in 13 days, and the other person was a biologist who was just carrying my rocks. And we did find that there were very interesting tephras, like this tephra here. And we were lucky enough to find a few roots from shrubs, but there are no trees on these islands because they're so windy. So it's very difficult to do the carbon dating. Okay, so we had a handful of dates showing us that there had been eruptions. We didn't even have proof that they were from Cleveland. It was pretty clear, but we did not have anything other than a suggestion that Cleveland had been active throughout the younger part of the Holocene, the most recent Holocene. So how do you put a timing on geochemical changes, on the frequency of eruption, if you can't even find anything to date? This brings me back to the absolute amazing opportunity to do interdisciplinary and multidisciplinary science. And I think actually this is a really responsible way to do science. It costs so much to get out to these islands and to spend a short amount of time there that we really should be facilitating all of the research we possibly can. So prehistoric people who still lived in the Aleutians and whose descendants continue to live in the Aleutians. I'm going to switch gears, tell you a little bit about the Unangak people. This is a photo from the 1940s, right before World War II, which itself was very devastating to the remaining culture of the Aleut people. It is so windy there that although the earliest inhabitants seem to have used lean-to or tent-like shelters, within about 1,000 years of arriving in the Aleutians, people had begun to live in semi-subterranean houses. They would dig a pit, these vary in size. They would use driftwood and whale ribs as supports. They would layer sod on top, and periodically, for cultural reasons that we can only guess at, when they decided to abandon a house, they would set it on fire and collapse the structure. So one of the really interesting things about the people who lived there, they lived near the coast. They depended very much on the maritime food system, but that might have made them vulnerable to tsunamis and to Holocene sea level change that was rising after the last ice age. Crucially, for my part of the story, I learned from anthropologists and archaeologists that people would bring crowberries that they would eat into the houses, and some of those crowberries would fall on the floor. And so you had a perfect carbon signal if you could sift through the houses and pull out the crowberries and then analyze those, because periodically volcanic eruptions would layer tephra over the top of these collapsed houses, which of course brings up the question, how well did people cope with volcanism? Okay, so let's learn a little bit about human migration. Genetic studies have shown that people started off here in the Chukotka and the Chukotka area of Siberia. There used to be controversy about, did people come from Kamchatka across the Aleutians, but archaeology studies over the last 20 to 30 years have really demonstrated that people must have come across the Bering at the land bridge, either making their way down the coast or an ice-free corridor, and then migrating out the Aleutians to the west. By nearly 9,000 years ago, they had arrived at 2 locations that are documented in the Eastern Aleutians. And we know that they made it to the far Western Aleutians by 3,500 years ago. My first work with archaeologists was on Adak Island, and we found one indication that people had reached for an initial colonization Adak about 7,000 years ago. So these islands of 4 mountains, we've got a 2,000-year gap in the migration history, and these islands of 4 mountains are right there, ready to be stepping stones. And so we felt that there could be a very interesting human story. People traveled in bidarkas and kayaks. And again, there have been various DNA studies showing that people, showing their affinity for other groups of people in the entire Beringia or Bering region. And we also see that there had to be 2 waves of migration of people into the Aleutians. That first wave of migration initiating around 9,000 years ago, but actually the Russians and later the Americans interrupted a second wave of migration that was happening only 1,000 years ago. Okay, so in terms of people learning to cope with volcanoes, of course, we all think of Pompeii and Herculaneum and the story from Italy, which is so exciting. And so this eruption of Casatoche in 2008 showed us directly how Aleutian volcanoes have this potential to devastate the ecosystem that people are relying on. These 2 photos on the left are of Casatoche in 2006 and 2005. And wildlife biologists were surveying birds out there. And so there was a small cabin, and we have a couple of rocky points that serve as markers for us. With only a few days warning, Casatoche erupted, and there were actually 2 bird biologists on this island at the outset of the eruption, and they were calling frantically to the Alaska Volcano Observatory to say, we're feeling a lot of earthquakes. We are smelling sulfur. We're really worried about this. But this area is so broad that there weren't enough seismometers to even affirm what the biologists were saying. And so we couldn't tell if these were volcanic generated earthquakes or tectonic generated earthquakes. Finally, these earthquakes became so overwhelming to the biologists that they called for help. And at considerable risk to themselves, a husband and wife team who are themselves of indigenous descent set out in their fishing boat in a storm and rescued these biologists. And within half an hour, pumice was raining on the deck of the ship. They just barely escaped in time. There's no sign of the cabin, and the area where the cabin was is now covered with 9 meters of tephra deposits. And you can see how much further the coastline extends. I bring this up because this story, as well as oral histories that I heard from people who live in Chile near Chaitén volcano, show that very often these precursor earthquakes are terrifying. And if you can leave, people will leave. And this is how people have been resilient to earthquakes, we think, because we see no evidence of a Pompeii type situation in this area. Okay, so I found it so difficult to get around on the volcanoes, and I had become acquainted with archaeologists. And so Dixie West and Bree McInnes, who studies tsunami deposits. Dixie is an archaeologist, and we had Tina Neal from the Alaska Volcano Observatory. And I am not, oh, and there's Jenny Hatfield, who's also an archaeologist and now the director of the Museum of the Aleutians. The 4 of us put together the first major project that was all women co-principal investigators for this area. It was a $1.6 million project. We had 2 different field seasons. We actually took undergraduates up there. It was amazing. We worked with paleoecologists primarily from Russia, as well as Mitsuru Okuno, our tephrochronologist. And we were taking a look at our knowledge that Nikolsky village, which is still an inhabited, largely indigenous village in the islands of 4 Mountains, was just across about 60 kilometers away from Mount Cleveland, which is here. Now, Samalga Pass is one of the most dangerous straits in the entire Aleutian arc. The water that daily changes direction and pours through this has actually provided a linguistic barrier. The languages are different on either side of this pass, different dialects, and shallow water fish species are different on either side of this pass. Yet you can see from one island to the next. If you were going to migrate, you could make it. Okay, so we know that humans did pay attention to their environment from wooden boxes on Kodiak that show what looks like could be a volcanic eruption generating tephra. So our project said, hey, we want to understand on these small islands how people were responding to paleoclimate and sea level rise, changing food sources, especially if there was an eruption, tsunamis, if that was a thing, post-glacial debris flows, volcanic eruptions. And then I was asked to do studies related to tool manufacture. I really should have brought a clock with me because I have, let me see if I can figure out what time it is.
Kirsten, don't worry for us. It's only for
Okay.
you because we are listening and we are enjoying it so much.
Okay, great. Well, stop me at any time with questions if you want. So this is a NASA image, and here we see the islands of four mountains in this yellow box. For those of you who are familiar with the television show Deadliest Catch, which the ships leave, the fishing boats leave from Dutch Harbor, Alaska. This is where Dutch Harbor is, and the community of Iliuliuk. Anyway, the only way to get to the islands of four mountains is to fly to Anchorage, stay overnight, get on board a ship, take the ship, which takes 12 to 24 hours based on weather to get out to these islands. And so you can see a really dramatic size difference in these islands. And we said, well, maybe the small land area would have really made people more vulnerable to these environmental changes that we were interested in. And did it require reliance on distant resources, such as obsidian for tools? And of course, this provided an opportunity for me for the first time to look into the history of these volcanoes and how they complete our story of the Aleutian Arc. This is a photo taken by Ken Wilson, who lived as a volunteer in the Unalaska community for a couple of years, published a wonderful book about the people. And he, on a flight, was able to get this amazing photo. We're looking approximately west here. Here's Mount Cleveland. Cleveland is attached to Tanna volcano by a narrow isthmus, and these two together are on Chuginadak Island. Carlisle volcano is here, Herbert is here. Where I did my master's is peeking out, and there are two more volcanoes out of view to the right. Before 2014, there had only been a very brief archaeological expedition to map out where the prehistoric villages were so that those lands could be given to the descendants of the people of this region. The rest of the land, unexpectedly, is part of a large, basically national park wildlife refuge, instead of being owned entirely by the Unalaska and Aleut corporations. So we had Cleveland, about which we had essentially a month worth of field work stretched over 3 seasons, and absolutely nothing known about these other 3 volcanoes in the area. We arranged to use the Maritime Maid ship because it has a helicopter deck. And so this is a photo of us coming in for a landing on the helicopter. And one of the things I'm very proud of is that we were able to partner with the US Geological Survey and the Alaska Volcano Observatory to install the first 2 seismometers on Chuginadak Island. It's very nerve-wracking to be in charge of many people's lives when there's an active volcano and there's no monitoring. And that's exactly what I had proposed, the scientific situation I had proposed to put us into. Once you have a helicopter, you get to have views like this. So here's Cleveland. And this is in 2015, I believe. And we had actually been delayed that summer from arriving by ship because of bad weather. And it turned out that that was probably a good thing, because the morning that we were arriving, we got a satellite phone call There were clouds everywhere. And the USGS folks said, we don't want to alarm you, but there's just been an eruption. And this paradoxically made me feel better, because Cleveland is going through a series of building small domes in the summit crater and then exploding those volcanic domes. And so to know that the pressure had been released right before we were going to be living and working within 5 kilometers of the volcano, that actually was very reassuring to me. The archaeologists maybe had a different perspective. Okay, so we had to set up a lot of temporary infrastructure. We had to set up a radio repeater station so that our 20 people, some on board ship and some about 14 scientists, so that we could work in different areas and contact each other. We set up the geophysical monitoring station, and we concurrently had geologists, archaeologists, paleoecologists, and paleoclimatology studies going all at once. This is the paleoecology team is here. These two are archaeologists, Ginny, Dixie, Kale, Dixie, Arkady, and Olga. And one of the responsible ways that people do archaeology there is they work very close to cliffs, or they look at the cliff face itself to see what is eroding, so that rather than having to do very careful digging, that it's very difficult to make much progress within a week or two, you instead can see the layers of sea urchins, Pacific cod bones, and the stones that people brought to use, we think, as griddle stones. And they were diving into the Bering water in this area to collect those sea urchins and placing their kayaks in this region. As you saw, I think from the paper I suggested, right? We had just in this ravine a beautiful set of stratigraphy that starts off in this alluvium that looks like a classic debris flow deposit. Maybe even a couple, and I'll mention some results of that. We get a big color change where we start to have the organic rich deposits related to people. And then we had this very nice set of tephras, including the CR02 ash that we managed to date as having occurred approximately 1,000 years before present. And for example, this is the floor of one of these houses with charcoal associated with burning and collapsing the house. And so this actual CR02 ash, Mitsuru Akuno estimates, was from an eruption as big as the Mount St. Helens eruption of 1980. And we would not have been able to date that nearly so well without this multidisciplinary study. Okay, and then on Carlisle Island, we did another, again, this is actually a beach cliff where we've cleared off, well, I didn't do it, some of my students helped, but the archaeologists did a very careful cleaning and measurement and documented midden deposits, right, with all the shells, griddle stones above and below. Here's that ash again. I think that's highlighted, yes. So this is a second village site with that CR02 eruption, classic tephrochronology, 2 distinct locations linked by this geologic deposit. And as you read, right, people clearly lived here prior to that eruption, and they lived here after that eruption. So we're getting an indication of resilience right away. My colleague Lyman Persico, who's a geomorphologist, took a look at the evidence for glaciation. So I'm throwing this in for you, Eric. Actually, the paleoclimate study is very poorly constrained, but we actually discovered a glacier on part of Chaginadak Island, which is here. And Lyman and his Whitman research assistant, Henry Landman, mapped out 2 moraines that are thought to be Little Ice Age moraines, because our estimate is that the neoglacial, approximately 3,000 years ago, the ice probably extended all the way to the ocean. The other thing that Lyman documented was, as the ice retreated and left all this loose material, you then had very active, what are called P-A-R-A, paraglacial processes, where there were debris flows that moved this material down slope. And so when we're seeing this very coarse alluvium in the bottom of these profiles, and we're able to date the house floor here, this gives us a timing for when these alluvial fans were being developed. We could not do this without the archaeologists. And we thought that these alluvial fans would turn out to be much older than they are, but they instead seem to be neoglacial alluvial fans. And here they are. So one of these archaeological profiles was clear up here, and you can see the very thick alluvium below this. Also here, this is more of the debris flow related to these glacial sediments moving. Here, we're getting a volcanic debris flow. You can tell these apart by how many lithologies you see in the clasts, how rounded the boulders are, nice, rounded, sub-rounded boulder here. These are much more angular. They show jigsaw fracturing, and they tend to be a single lithology. So we didn't have a lot of time to look into that, but these are, geology skills from my undergraduate days were leading me to make supporting observations that were very helpful. So what we found, right, if we're looking at the Holocene and thinking about paleoclimate, so here's today at the left, and here's basically the start of the Holocene. We have Unangach occupation of some islands. This is Unalaska, this is Adak. And we expected to find that the occupation of the islands of Four Mountains would be right in between. And instead, our archaeological evidence for human occupation is here, almost 4,000 years ago, 3,000 years younger than we expected. And so one of our inferences is that perhaps these debris flow deposits either covered earlier habitations, or maybe these islands were not really suitable for year-round occupation before then. Really intriguing work by the Russian team looking at stable isotopes in bog deposits show that humans started eating bird eggs actually on these islands about 7,000 years ago, which was what we expected to find. That was the timing we expected to find. But we don't know if they were eating those bird eggs seasonally, just coming over from an adjacent Nikolsky village area, or whether they were actually living on the islands at that time. So there's still lots of puzzles. So Lyman was able to publish this, and we have 2 Whitman student co-authors, which is really fun. Just very quickly, before I get to more of the Tephra chronology story, this subduction zone makes very large earthquakes, magnitude 8.2 in 1938, 8.2 in 1946, 8.6 in 1957. And this 1957 earthquake actually created a tsunami that caused damage to Hawaii. So we were looking for evidence that people might have been impacted by tsunamis in the islands of Four Mountains. And we were trying to determine how many tsunamis there might have been in the last 3,000 to 5,000 years in order to understand more for our own safety. How often do big tsunamis happen here? So that was the work of Bree McInnes, a sedimentologist at Central Washington University. And she was able to find some tsunami deposits and correlate them. She was able to find logs from that 1957 earthquake and determine that it had been much larger in this area than previously estimated. However, this stuff was a nightmare to dig through on these beaches. These beaches are cobble rich, and it was very difficult to dig these trenches and find these deposits. And the OSL dating that we attempted was unsuccessful. So we know there were some tsunamis, but we as yet do not have any timing for when those paleo tsunamis happened. Okay, so just a quick summary because we're covering a huge amount of ground. We worked in 3 different prehistoric villages, and we found that they had been occupied since about 3,800 years ago. You read about that. We found that there were paraglacial debris flows below that, which were either inhospitable to permanent settlement for a while, or there's been a huge amount of erosion of these alluvial fans. And so maybe that earlier set of villages has been lost to erosion or buried. And as it turned out, this 1957 tsunami was so big, it gave us the maximum reach inland that a big tsunami would make it. And if you were paying attention to how high those beach cliffs were, the people seem to have chosen those locations for a reason. It's easier to dig your village. However, possibly it may have been that they were staying so high to stay away from tsunamis. The villages were always higher than our maximum tsunami evidence from 1957, which was nearly a magnitude 9 earthquake, as it turns out, in this area. So, and then the other thing you'll notice throughout the Aleutians is people built their villages largely on the Bering side, not on the Pacific facing side. There are a few exceptions, but if you want to be away from both the prevailing wind direction and away from those big tsunamis, they picked the right locations. Okay, more back to volcanoes. Shall we take a break for a moment? Do you have questions so far?
I don't know, guys. You have questions so far, or we want to just go and see until the end and ask as you wish? I think maybe it's better.
Okay.
We go ahead. I don't know.
Okay. Well, we had taken a look at a village on this part of Tanna, and we had taken a look at a village on the north side of Tanna and 2 village sites on Carlisle, although we did not have very much time at one of those. There were also 2 village sites on Herbert. Not surprisingly, there is no indication of a village site on the Cleveland flanks. But the eruptive history of these 3 volcanoes were totally unconstrained. So we had this question, were they all erupting, taking turns erupting in the Holocene? Could we locate big tephras and match them up with their volcanic vent? And then could we look at the tephra stratigraphy in the villages, partly to date that tephra stratigraphy and to think about resilience? So even though I'm a geochemist, I spent a lot of time being project leader and dealing with logistics. I spent a lot of time looking for obsidian that people would have used as tools. That was my specific part of this project, was to look into the tool making materials. And in looking for obsidian, that took us everywhere on these islands. That was great because as a geochemist, I also wanted to get as many samples as I could. I see there's a comment maybe in the chat. Okay, great. Bye, Christine. I think I missed Christine. Okay. Okay, so one of the really dramatic things, remember I had been on the island in 2002 and 2004 and walking around the flanks. And to get there in 2014 and see these massive, massive volcanic bombs. These definitely flew through the air and fractured on impact. You can see how big this one is. This one at the lower right looked like this giant slug of lava that was the size of a Volkswagen. This was really very big. And speaking of resilience, where these cracked open and oozed out a highly vesicular interior, that traps moisture as well as little seeds and spores very readily. So we could already see 6 years later how the vegetation was starting to recolonize. We did all credit to Tina Neal, who just recently retired from being the head scientist at the Hawaii Volcano Observatory. Tina Neal worked with us in 2014, which was fabulous. She and Pavel found a fabulous tephrochronology section. These are Pavel's data as to what the compositions of these layers were. And they were also collecting soils to try and get carbon-14 on the soils. So here is the 2001, that initial February, March 2001 eruption that sparked the initial interest. But they also found actually more than 60 tephras. We don't know which ones they are all from, but we see that the record goes back 10,000 years. This is what it looks like. Here's that about 6 centimeters of the 2001 eruption. Here are their markers as they sample as many of these 60 ashes as they could. They saw 4 sizable eruptions in that 10,000 year stratigraphy. One of the exciting things when you get to the bottom of that particular tephra section, and that tephra section was up a little ravine here, it turned out that they were able to get a basal soil and find a very thick scoriaceous tephra. And their analyses of this tephra matched my analyses of this cinder cone. So we learned that the formation of this fox trail cinder cone that eruption took place slightly younger than 9,500 years ago. So we're starting to build this, this story. There was a really significant rhyolitic explosive eruption. We're not exactly sure where this comes from, but it may come from the east side of Tana. We think that's where it comes from. And this eruption was about 7,000 years ago. In other words, these volcanoes are active concurrently. To our surprise, we found that Tana volcano has active fumaroles and mud pots. We see that Kagamo volcano nearby also has active fumaroles. We see that Herbert volcano, we think that eruption also happened about 9,000 years ago, and there are active fumaroles. In other words, we have at least 4, if not 5 volcanoes active in the Holocene. I'll come back to that at the end. We've been able to look at chemical elements like potassium, rubidium, and barium rubidium, and see that these volcanoes have their own geochemical fingerprint. Sometimes that fingerprint overlaps. Here's Cleveland in green, overlapping with Herbert, but Carlisle volcano actually has quite a different composition, as do some of Tana vents. Okay, so I'm still working on this project. This is an example of how the ashes from Cleveland make one compositional trend. The ashes from Tana make a different compositional trend. And so although we need to do more sampling and more carbon dating, it does look like we will be able to distinguish at least as many of the eruptions from these 2 volcanoes. And this Neapolitan is that very rhyolitic eruption from 7,000 years ago. So when we're doing tephra chronology, just to reiterate, we need to do our basic geology. We need to get out on the landscape. We need to find the tephras. We need to measure thickness. We need to look at their locations relative to where these big vents are. We need to analyze the glasses and the minerals so that we can distinguish individual ash layers from each other. We need an identity for them. And then we need the carbon-14 dating to help us put together the timing of these. Here, Tana has a small caldera, well, a small summit crater that is from a big eruption. Those glaciers that I pointed out to you are over here in this valley. And I actually think that maybe that 7,000-year-old eruption is related to this collapse of the flank over here, because we have some ignimbrite, some welded tuff that we found over here. And that will actually be the reason that we try to go back to Cleveland, not this summer, but next summer, 2022, if we get our funding. But we did find lots of evidence that Tana, thought to be completely Pleistocene and not a threat, has a pretty robust Holocene history. The USGS is very interested in further assessing Tana's history. This is just showing you that a couple of my students are assisting Dr. Ginny Hatfield in the archaeological excavation and those beach cliffs. And I'm bringing us back to this 1,000-year-old ash. we had a lot of great carbon-14 dates related to when this ash happened, thanks to the archaeologists and paleoecologists. Mitsuru is someone who does the carbon-14 dating. Pavel is someone who has an electron microprobe and obtained the analyses. My part of this as a geochemist was to use statistics, in this case, what's called a principal component analysis, to look at how closely these compositions of the tephras match. So you can make one diagram, potassium versus barium, or magnesium oxide versus silicon oxide, but you have to make a whole lot of diagrams, and it kind of makes you cross-eyed to try and compare, are these matching up across all these diagrams? So instead, 9 of these major elements, magnesium, silicon, potassium, sodium, aluminum, etc., all of those variables are treated together in the principal components analysis. It lets you compare all your chemical information at once, okay? And it turns out that principal component 1 is telling us mostly about these 4 variables because they are correlated. And principal component 2 is telling us mostly about these 3 correlated variables, okay? And that CR02 ash actually consists of 4 layers. And I have to move all the faces, okay? S4 is the lowermost layer, S1 is the top layer, and S2 is the coarsest, thickest layer. Okay, so you see really nice overlap of the compositions of 2 of these layers. Okay, where did we go? Mitsuru walked, I mean, we took the helicopter, and while I was looking for obsidians and doing geochemical sampling, Mitsuru was carefully sampling the tephras in these locations. And from the field characteristics of the sequence of 4 ashes, with one being much coarser, he was able to say, all right, I've correlated stratigraphically this deposit that I think is the same in all these areas. And this was going to allow us to ask the question, remember, he determined the age, but we needed to locate the vent. Was this an eruption from Herbert, from Carlisle, from Cleveland, from the cinder cones, or this part of Tana? Okay, so we went to these different locations, the Tana location, there were multiple ash layers, the Herbert location, and we were able to correlate several of those locations either with the 2 related ashes that sandwich the Lapilli tephra or the Lapilli tephra itself. We were trying to match those 3 layers. And part of what was crucial is that finding these ashes in a peat bog where you can take a continuous core and there's a lot of organic material. And so we also compared the compositions of this tephra, not only at these locations, but in the peat bog. Now, the peat bog is having lots of stuff wash into it, so you can get glass shards that may not look very similar to your sample. You're getting a mixture in your peat bog, but we did get some good matches to our peat bog samples. Okay, and this shows you what that peat bog looks like. There's Lyman Persico with 2 Whitman students. Here's Mitsuru, and they drilled into the peat bog. Here's the stratigraphy of the peat bog, showing some really prominent eruptions. And this is that CR02 tephra. So in addition to the information from the villages, we had carbon dates from right below the tephra and right above the tephra, showing nicely that approximately 1,000 year before present age. Okay. The black triangles here are all the possible source vents. Carlisle is much more eroded and does not look like it has an obvious Holocene history, except perhaps for one lava flow over here. So we have, thanks to all the geochemical sampling that Pavel and I did, we had compositions of all these possible source vents. And what we found was the composition of Cleveland glass, which is here in these triangles, from 2001, the Cleveland glass from 2001, and we have Cleveland whole rock. The Cleveland glass is what best matches this sizable lapilli tephra from this 1,000-year-old eruption. We did also compare these other compositions. Here's Herbert, this one, it's an outlier. We have these cinder cones here. They are not as good a match. Unasca here, not as good a match. Cleveland really looks like the culprit for this particular eruption. We then took a look, again, this is Mitsuru's work. He was looking at the thickness of that lapilli tephra in all the locations he could find it. And as you can see, the greatest thicknesses, 12, 13 centimeters, 18 centimeters, the greatest thicknesses are right here on the flanks of Cleveland, whereas it's definitely too thin near Tana. It does look like maybe the wind had a northwesterly direction to it during that eruption. So keeping in mind that we were looking at a prehistoric village in this region, one in this region, one in this region, and one in this region, right? We can see that if you're over here, that eruption might have been very frightening, but the amount of ash was very thin. However, on Carlisle volcano, this could have been a big problem for the people living on that volcano. So you know kind of the summary from that paper, which is lots of evidence of people living in these villages. And here we're talking about one specific village that we can see where all the lush vegetation is, and the outline of some of these house pits, the Barabaras. Lots of evidence of occupation prior to that lapilli tephra, that 1,000-year BP eruption, and lots of evidence that people came back eventually. And our last evidence of occupation affirms the devastation of the interaction with the Russian people. Although there were occasional hunters and trappers who would come to the islands in recent times, the occupation history essentially ends 250 years ago. And this is just a graph that is showing this story for many of the villages. So one village is orange, one village is red, one village is green. If you want to take a look at how large an area of people responded to this eruption, what you can see is none of these villages have any evidence for occupation during that eruption about 1,000 years ago. They really seem to have left a little bit before then even. There's a second interruption at an older, about 2,000 years ago, when a neighboring island had a caldera forming eruption. I'm going to skip over that. So if we go back to some of our initial questions, what did we find? We found evidence for frequent Holocene eruptions and that at least 3 of these volcanoes were active in the Holocene. Were the habitation sites influenced by volcanism? Yes, especially these 2 eruptions. However, the villages were reestablished. The other thing I can say very quickly is that when you look at the tools and the refuse that's left behind, this is not a Pompeii situation. There's no sign of lots of bodies. There's no sign that precious tools were in there, that they were in use shortly by this eruption. People had time to take their material goods with them before this eruption. Just in terms of future research directions, a lot of people are very excited about what the geophysics is starting to show. And it's really showing that it looks like the magmatic conduit, the magmatic system of Cleveland is very open right now. And that's somewhat unusual to show that throughout the crust, really stretching down 8 or 9 kilometers, that there might be a fairly open system. This means you can have eruptions with relatively little warning. I mentioned that ignimbrite that we found over on Tana, so people asked me my opinion of this ignimbrite, and Pavel and I knew that it had to come from a really big caldera. And I had often thought about why would you have so many big stratovolcanoes in such a small area? And so I said, I think that possibly there is a submarine caldera here. And these volcanoes have continued their growth along the rim of that volcano. Well, some evidence from the geophysicist is now corroborating that. And John Power just published a paper that he very kindly asked me to be a co-author on, this geophysics paper. This came out this month or last month, anyway, 2021. And we think we see data in the gravity signature that might support my hypothesis that there's a big submarine caldera here. So this is the focus of a proposal at NSF. We hope it will fund us to go back and do more of a geophysics, geochemistry study of this area. That's it. Thank you for paying attention to what was probably 2 talks instead of just 1. But I'm happy to take questions.
Thank you, Kirsten. Let's, it has been worth to wait